Uh, I'm Omar, and I'm here to spot the light on the correlation consistent effective core potentials. Usually, you will hear me refer to as CCECPs. Uh, what distincts CCECPs from previous effective core potentials is that we infuse correlation and relativistic effects by constructing it within many-body methods, which serves our purpose of highly accurate quantum Monte Carlo and quantum chemistry calculation. This is also a fundamental leap from the mean field approaches that previous ECPs used. And in a sense, our philosophy is to take the simplest possible model and we look at the limit of how accurate this is. And very often we can push its accuracy orders of magnitude better than other models used in previous generations. I'll come back to accuracy validation later in my talk, but of course, using Gaussians allow ECP integral evaluations to leverage the existing highly optimized machinery within Gaussian-based codes. Critically, we enforce finite wave function cusp conditions at the nucleus, ensuring very smooth finite potential functions similar to the one just presented, regardless of the core size, which is computationally saving for quantum Monte Carlo as it significantly reduces the fluctuations. And in periodic codes, those allow lower kinetic energy cutoffs to be used. Going quickly over the CCECP, average relativistic effective core potential, which doesn't contain explicit spin orbit functions, but I'll talk about that later as well. Here, we have a local part depending only on the distance between the electron and the nucleus, and non-local part that depends on the angular momentum. For the local potential, so the local potential in a sense tunes everything. We choose a well-established form that is non-singular and behaves quadratically at the origin and is parameterized by a short sum of radial powers multiplied by Gaussians. The non-local potential adds angular momentum dependent corrections to accurately reproduce the different core screening and relativistic effects experienced by valence electrons in different orbitals, so the s orbitals, p orbitals, and so on. All the coefficients and exponents donated by Greek letters here, like the alphas and betas, are our optimization parameters. And what you will typically find if you took a look at the parameter files, that is, so on the right here, I have an example for silicon, and you need not to worry about the values here, but you will typically find you'll find it divided into a local potential channel and a non-local potential channels with 3 coulombs that correspond to the radial powers, the exponents, and the coefficients. So back to how we infuse correlation and scalar relativity in CCECPs. Well, it's actually quite a laborious process as the CCECPs undergo a battery of transferability tests against couple clustered singles, doubles, and perturbative triples, all electron reference as our many-body benchmark. And here I actually mean 2 aspects by transferability. So first, the atomic spectra in the neutral atom, electron affinity, ionization potentials, all are reproduced with sub-millihartree deviations, proving transferability across ionization limits. And we don't stop there. We stress test the transferability through binding energy curves across non-equilibrium configurations. This ensures the pseudopotentials retain fidelity even in strongly correlated and distorted environments. The second part, the second type of transferability, which I mean, is ensuring that the climate bilander form of the CCECP, which is required for plane wave codes, reproduces the accuracy of our reference semi-local potential. We test them in plane wave codes to determine required energy cutoffs. And on average, it's about 60 Rydbergs for large core main group elements, about 200 for the small core versions, and 350 for the transition metals, and about 400 Rydbergs for the lanthanides. Finally, we also established benchmark reference data that's exact or nearly exact for correlation, kinetic, and total energies of atoms represented by our CCECPs. And then we can quantify the locality and fixed node biases for the single reference fixed node DMC. So this slide benchmarks CCECPs against an all-electron reference for lead oxide molecule. And lead here is a heavy system where your relativistic contractions and core valence correlation dominate. And on the figure in the figure on the left, we see in black the data points calculated across various bond lengths using a total of 90 electrons. And in green, you find the data points calculated using CCECPs with only 6 electrons. You understand, like the all electron calculation took more than 70 times longer to finish. And the end results, CCECPs track the all electron Morse potential fit curve, and they are almost overlapping on top of each other. Okay, so let's take a moment, move to the figure on the right. Here I calculated the discrepancy between CCECPs and the all-electron reference, converted the units to electron volts, and you can see the gray band here represent chemical accuracy, which is about 43 millieVs. And you can clearly observe how the CCECPs maintain accuracy across geometries, and basically the CCECP consistently achieves the chemical accuracy threshold. So finally, to model spin orbit effects in the valence space, we designed pseudopotentials acting on both orbital and total angular momentum quantum numbers. So using a two-component spinor formalism, we generate spin orbit relativistic effective core potentials, which are an average relativistic effective core potentials that I talked about in the last slides. And we add spin orbit terms, and that way we can actually reproduce the full Dirac spectrum. So contrast with scalar relativity, the average relativistic effective core potential is a static one-component calculation that averages spin orbit effects weighted by orbital angular momentum, and the spin orbit relativistic effective core potential that includes the spin orbit terms has the true component relativistic is the true component relativistic pseudopotentials, which contains like explicit treatment of spin orbits in the valence Hamiltonian. So since their introduction in 2017, CCECPs had seen systematic development. To date, we have completed nearly 60% of the periodic table. So everything here in black or bounded by a red box are elements that we had completed. You can access them through our website, pseudopotentiallibrary.org. It's an open source. You feel free to add your requests there. So if you go into one of the elements, what you'd usually see is sometimes we add multiple core choices for an element. So this is silicon, and we have multiple core options that would serve like applications better, that like different applications more or less. We also offer format support for the quantum chemistry codes, especially the ones integrated with QMCPACK. We include optimized correlation consistent Gaussian basis sets, up to 6 zeta sometimes. But at the very end, you'd usually find the CCECP parameter files in its semi-local format, including the radial grid beads XML used in QMCPACK. Also, finally, we have the Kleiman Bilander UPF versions of the plane wave codes. And we also include an RPT file that contains relevant information about the conversion and the transferability. Just one thing to note is for heavier elements where we have added the spin orbit terms, you'd find we distinct between them. So you'd have ccecp.arab and ccecp.sorab. So this is something to note when you are using them. And you can directly access the website or use the command line with the wget command to download the files. And this is my final slide that contains the links and the papers from 2017 till our very recent efforts, which is currently on archive. And that's everything I have for you today.
Thank you, Omar, and also Lubosh. So presentations are open for any questions or discussion. And while people are typing or thinking of their question, I'll start with a question for Lubosh. And that is, there was some discussion of using pseudopotentials for larger Z or Z atoms, but what is larger Z or Z? So where is all electron practical? Would one always use a pseudopotential unless, say, doing something very, very difficult or very challenging for accuracy-wise on the first row? What's your recommendations?
So that's a good question. So let's start with the first row. You can do pseudo potentials with the, say, static from boron with the helium core. But you have another option. Imagine that you want properties which will be strongly influenced by the sort of a shallow core in the boron atom, namely, for example, boron under the very high pressure in a particular type of a solid. Suddenly the 1s states would contribute. So what we offer is that you would have all electrons, but there would be no cusp. Namely, the Coulomb potential would be smoothed out at the origin. Everything gets much more smoother, although you reproduce practically all electron properties without having a Coulomb singularity. Therefore, you can use smooth Gaussian basis sets with much smaller number of basis functions. You could, in principle, crank up also plane waves and try to use it if you want to. So that would be sort of a response on a first row. Second row, like a silicon, you have three types of options. That would be 4 valence electrons, which would be on neon core, another semi-core electrons inside, where you eliminate only 1 s2 electrons, namely instead of 4, you will have 12. And that would be the helium core. And then you can have also the smooth out all electron if you want to. And now these all three options, say on the silicon atom, would make sense in not too large of a system. But imagine that you want to do a copper surface. And it has 12 atoms at minimum within some supercell and some symmetry. Suddenly, all electron calculation is essentially ruled out, and you are only in the third row. Because simply the energy is 1,600, and basically just calculating the energy of the system would be prohibitively expensive. So roughly from the beyond the 3D atoms, it's impossible not to use ECPs, and more or less this would be true not only for QMC, but for most of the one particle methods, just because of practical reasons. Definitely for plane wave codes. In fact, plane wave codes have very often limits on cutoffs, and those could be actually kind of a problematic for some type of properties. So one have to do more checks. With the advantage of CCECPs is that those checks have been done, and therefore you know what you are actually using without doing any more checks in that direction. Now, I tried elements with Z equal more than 100, which are, of course, academic exercises for, say, like an organism or something like that, with Z equal to 118. There, it's almost impossible to run the traditional DMC algorithm at all. It just doesn't work. The fluctuations overwhelm the whole thing, and it's impossible to use that. I don't know whether this is a satisfactory answer, but this is roughly the experience which I had.